In this video, we're going to continue learning about derivatives of functions, but we're going to learn some shortcuts to make it much easier to find the derivatives rather than using that complicated limit definition we learned in the last video. So let's just start by learning some basic differentiation formulas. One thing that we can use is called the constant rule. And the constant rule says that the derivative with respect to x of a constant is equal to 0 every single time. What this means is if you have a function f of x equals some number, so let's just go with f of x equals 12, then f prime of x, the derivative of f, would be equal to 0. Another very important rule for us is called the power rule. And the power rule says that if n is a real number, then if f of x equals x to the n power, we have the derivative of f prime of x, is equal to n times x to the n minus 1 power. So you get to bring the power down, multiply in front, and then your new power is going to be 1 smaller. Let's just do some examples that only use these two rules right now, our constant rule and our power rule. So example, we're going to find a whole bunch of derivatives. So our first one is going to be find the derivative of f of x equals 5. Well, f of x equals 5 is a constant function, and we know from the constant rule that that means the derivative is going to be equal to 0. How about if f of x equals x to the 5th? Well, before this video, you would see this and you would have to do the limit as h approaches 0 of x plus h to the 5th minus x to the 5th all over h. And you would have to, for that x plus h to the 5th, do a whole lot of distribution, combining like terms before you could get the answer. But now we have our power rule. And the power rule says that the derivative of x to a power is equal to that power times x to the n minus 1 power, so 1 smaller. I get to bring the 5 down in front, then I have x to the 4th power because 4 is 1 smaller than our previous power. Way quicker than using the limit definition. Next one, if I have f of x equals pi, what is the derivative? Well, pi is still a constant, even though it's kind of a complicated constant. So my constant rule says that the derivative is going to be 0. How about this one? F of x equals x. Well, x is not a constant, so it's not the constant rule. We have to think about this one using the power rule. But it doesn't look like there's a power there, but there still is one. What is the power there? The power is going to be a 1. I'm just going to put that in green just to let us know what we're thinking of. F of x equals x is the same thing as f of x equals x to the 1st power. So by the power rule, I know that I can bring that power down and then multiply by x to the 0 power because that's 1 smaller. But anything to the 0 power is going to be 1. So this simplifies to f prime of x is equal to 1. So that one still uses just our power rule. Sometimes that rule, that the derivative of x is equal to 1, it's taught as a separate rule. I like to teach it just with the power rule because it's less that you have to memorize. It's still the same rule. All right, we still have a few more parts for this example. How about, this one's starting to get a little more complicated. What if my function is the square root of x? And I want to remind you, in our last video, we found this derivative using the limit definition. So you can compare our result this way to the one in the last video, and you'll see that they're the same exact thing. So this one, we know square root of x is not a constant, so I'm going to have to use my power rule in some way. So the first thing I would do is I would rewrite this as x to the 1/2 power, because now it's a little easier to use my power rule. Using my power rule, the 1/2 gets to come down, and then my x has a new power, which is 1 smaller. 1/2 minus 1 is -1/2. So this is technically the answer, but I'm going to rewrite it a little bit just to show you it's the same thing we got in our last video. Remember, having a negative power means you can rewrite it in the denominator as a positive power. And then if I just do one more thing, it's going to look exactly like the answer we got with the limit definition. Rewrite the x to the 1/2 as a square root again. And that is the answer that we got last time using that whole limit of f of x plus h minus f of x all over h. It's just a lot quicker using the power rule. All right, let's do just 2 more. Part F. We have f of x equals 1 over x squared. So first thing we should do is rewrite this so it just looks like x to a power. So I can rewrite this using a negative exponent, x to the -2. Then when I take the derivative, the -2 comes down. My new power is 1 smaller. So I get -2, x to the -3. You can leave your answer like that if you would like, or you can write it with the x to the 3rd in the denominator again. And the last one, f of x equals pi to the 3rd. So a bunch of you right now are going to be tricked by this one, and that's okay. It was actually designed to trick you. A bunch of you will also get it right. So there are 2 possible answers I can imagine you getting out there. One of the answers is 0, and the other answer is 3 pi squared. And only one of those is correct. The correct answer is that the derivative is equal to 0, because pi to the 3rd is still a constant, and the derivative of a constant is 0. This is not x to the 3rd power, so it doesn't get to use that power rule. All right, so that's how we use our power rule and our constant rule. And of course, we have a couple other rules that we need to learn as well. So the constant multiple rule. The constant multiple rule says the derivative with respect to x of a constant times a function is equal to a constant times your derivative f prime of x. So the constant just gets multiplied in the front. The sum and difference rule says that if you have the derivative of one function plus or minus another function, you can take the derivative of each function separately and just add or subtract the results. So this comes in handy because our power rule and our constant rule really only gives you a way to do things that just have one term. And now we'll be able to differentiate lots of different terms all at once. Let's do an example utilizing these rules. We are going to differentiate, and that just means find the derivative. The function f of x equals x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x to the 3rd minus 6x plus 5. So before I actually find the derivative of this function, I'd just like you to imagine for a second that we were going to do this using the definition of the derivative. Picture having a limit as h approaches 0 of f of x plus h minus f of x all over h. And picture how terrible and tedious all of that distribution would be for this incredibly long function. If I had us doing it that way, you'd probably be closing out of this video right now and moving on to something else, because who wants to waste their time like that? But now that we know about our power rule, and we know that when we have adding and subtracting inside of our function, we can take the derivative of each piece individually, this ends up being a super quick problem. For the x to the 8th, I get to use my power rule. The 8 comes down, my new power is 1 smaller, so I get 8x to the 7th. Plus, now I have to do the derivative of 12x to the 5th. We know from our constant multiple rule that the 12 is going to stay there multiplied in the front. And then the derivative of x to the 5th, I use my power rule, the 5 comes down, and my new power is 1 smaller. So I get 12 times 5x to the 4th. Now I have a minus 4. That constant gets to stay there, and the derivative of x to the 4th, 4x to the 3rd. You bring the power down, and your new power is 1 smaller. Derivative of 10x to the 3rd, my 10 gets to stay from my constant multiple rule, and the derivative of x to the 3rd, 3 comes down, and my new power is 1 smaller, 3x squared. Now I have this other one here, minus 6x. So the minus 6 stays, and I would have the derivative of x. If you remember from our previous example, the derivative of x is 1. You could get that by using your power rule. It has a power of 1, bring it down, and you would have x to the 0 power, which is also 1. And then that derivative of 5 is a constant, so the derivative is 0. So here's my derivative. I just have to simplify it a little bit. And I get 8x to the 7th plus 60x to the 4th minus 16x to the 3rd plus 30x squared minus 6. And that's all there is to it. Not too bad, way, way easier than doing it by the limit definition. I don't even want to do this one by the limit definition. This is so much quicker. And you might be wondering why it is that we're allowed to even do this rather than using the limit definition. And the reason we're allowed to do this is because actually all of these rules that we're learning can be proven using the definition of the derivative. The proofs can sometimes be a little long and hard to follow, but there is sound mathematical proofs that show that these rules are always true. So once the rules are proven to be true, why do we torture ourselves with the definition? There's no need. We can just go ahead and use the rules that we know will always work. Let's do another example. This one's going to be a little more complicated. Find the points on the curve y equals x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. All right, so before we start this problem, we just need to do a little bit of thinking. What do we know about tangent lines? We know the slope of the tangent line is equal to the derivative of the function. So I'm going to need to take a derivative to find the slope. Now, what do we know about horizontal lines? Horizontal lines have slope 0. So this is asking us to find where the slope of the tangent line is 0. So we need the slope of the tangent line to be equal to 0, and that means we want to solve the derivative is equal to 0. And that will give us all of the x-coordinates of the points we're looking for. So we're going to need to take a derivative of this function, set it equal to 0, solve for x, and then to find the y-coordinates of the points, we plug the x's that we find back into the original equation. So let's start by finding the derivative. What is the derivative of y? Well, I have an x to the fourth, so that's a power rule, 4x to the third. Remember, the power comes down and the new power is 1 smaller. Now I have 6 times an x squared. My 6 gets to stay. Derivative of x squared is 2x to the first, using my power rule. And the derivative of that 4 is 0. So now I have my derivative. I can set it equal to 0 to figure out the x-coordinates of the points where my tangent line is horizontal. So we have 4x to the third minus 12x, just by multiplying the 6 and the 2 together, equals 0. And this is what we need to solve to find the x-coordinates of our points. I would solve this by factoring. I can pull out the greatest common factor of 4x, which leaves an x squared minus 3 in parentheses. And this gives me either 4x is 0 or x squared minus 3 is 0. So I get x equals 0 as one of my x-coordinates. And then to solve this guy, we're going to add 3 to the other side and take a square root. So I get x's plus or minus the square root of 3. So I have 3 x-coordinates where my tangent line is horizontal. So we need to find all 3 y-coordinates to answer the question. The question wanted the points where the tangent line is horizontal, and all we have so far is just the x-coordinate of those points. So we still need to find the y-coordinates. And we do that by plugging into our original equation, which was y equals x to the fourth minus 6x squared plus 4. So when I have x equals 0, y is equal to 0 to the fourth minus 6 times 0 squared plus 4, which is 4. When x is positive square root 3, y is equal to positive square root 3 to the fourth minus 6 times positive square root 3 squared plus 4, which that is 9 minus 18 plus 4, which all equals negative 5. And then the y-coordinate for x equals negative square root 3 We have y equals negative square root 3 to the 4th minus 6 times negative square root 3 squared plus 4. And this ends up also equaling negative 5. So the 3 points for my tangent line is horizontal are 0, 4, square root 3, negative 5, and negative square root 3, negative 5. And those are where my tangent line is horizontal. So that's pretty nice. It would have been a lot harder to do that just using our definition of the derivative, like what we did in the last video. All right, so now we're going to learn just a couple derivatives of some trig functions. We'll learn some more in the next video. But we're going to talk about just the derivative of sine and cosine. So the derivative of sine of x is equal to cosine of x. And the derivative of cosine of x is equal to the negative sine of x. I would suggest that you memorize these two derivatives as well as the derivatives of the other trig functions once we get to them in the next video. These would be a little more complicated to try to derive with the actual limit definition, so I would just go ahead and memorize them. Derivative of sine is cosine, derivative of cosine is negative sine. Let's do an example where we have some trig in our problem. Let's differentiate y equals 3 sine of theta plus 4 cosine of theta. So don't be concerned about the thetas. So we're just using theta instead of x. We still do the derivatives the exact same way. And so to take this derivative, I'm going to be using those derivatives of sine and cosine, as well as using my constant multiple rule. So I have this 3 that gets to stay there. Derivative of sine is cosine. My 4 gets to stay, and the derivative of cosine is negative sine. So rewriting this just a little bit, I get my derivative y prime is 3 cosine theta minus 4 sine theta. All right, well, that's not too bad. So in the last video, we also talked about how we have higher order derivatives, second derivatives, third derivatives, fourth derivatives, and now we can use these rules to calculate those rather than using the definition. So we're going to do an example of finding a higher order derivative of one of these trig functions. But we're going to have some fun. We're not going to find the second derivative, third, or even fourth derivative. We're going to find the 27th derivative of f of x equals cosine of x. So there's a couple ways we can do this. You can literally just take the derivative 27 times if you want. There's nothing wrong with that. But if we start trying to do that, you might notice a pattern that will help you save a little bit of time. So let's just take a look at what happens when we start taking the derivative. have f of x is cosine. So my first derivative, using our rule, is negative sine. My second derivative, my negative would get to stay there by my constant multiple rule, and the derivative of sine is cosine, so I get negative cosine. My third derivative, my negative would stay, and I would have derivative of cosine is negative sine. So when I simplify, I get positive sine. And then what would be the fourth derivative? Well, my fourth derivative is the derivative of sine, which is cosine. And so I'm back where I started. So I have a pattern. It's going to go cosine, negative cosine, sine. Cosine, negative cosine, sine. And just keeps repeating. So notice my fourth derivative got me back to cosine. The pattern's going to repeat. And so I know that the next time I get cosine will be after another 4 derivatives. So we are already at the fourth derivative. So we would have the fifth derivative is going to put us at back to negative sine. The sixth derivative will be back at negative cosine. Seventh derivative would be sine, and my eighth derivative would be cosine. So I know every 4 derivatives, I'm back where I started. So I have my fourth derivative is cosine, my eighth derivative is cosine, my 12th, my 16th, my 20th, and my 24th derivative are all cosine. So I'm going to start with the 24th derivative, because I wanted the 27th derivative. So I'm at the 24th, now I only have to do a few derivatives to get to my answer. My 25th derivative would be the derivative of cosine. We're back to negative sine. My 26th derivative, we're back to negative cosine. And now the one they wanted, the 27th derivative, is the derivative of negative cosine. We're still following the same pattern, and we're at positive sine. So that's something super nice about the derivatives of sine and cosine, is that they repeat with a pattern. So you can get some really high order derivatives pretty simply by just noticing the pattern and taking some shortcuts. Let's see, we're going to finish this video off with a very long problem. It has multiple parts, and we're going to deal with having velocity and acceleration and things like that again. So an example. The position of a particle in meters is given by f of t equals t to the third minus 6t squared plus 9t, where t is time in seconds. Part A. What is the velocity after 2 seconds? And how about after 4 seconds? Well, now we have to remember how do we find the instantaneous velocity given a position function? The velocity is equal to the derivative of our position. So to find my velocity, I need to take the derivative of my function f. So my velocity is equal to the derivative of this guy. The derivative of t to the third using my power rule is 3t squared. 3 comes down and my new power is 1 smaller. The derivative of this minus 6t squared, your minus 6 gets to stay. Derivative of t squared is 2t to the first. And then my derivative of 9t, the 9 gets to stay, and the derivative of just t is 1, using what we used earlier in the video, or you could use a power rule again. So let's simplify this velocity, and then we will figure out the velocity after 2 seconds and after 4 seconds. So simplifying this velocity, I get 3t squared minus 12t plus 9. And so my velocity after 2 seconds can be found by plugging a 2 in. So I get my, let's see, this would be 12 minus 24 plus 9, and we get negative 3 meters per second. And then my velocity after 4 seconds, we have 3 times 4 squared minus 12 times 4 plus 9. And that is equal to 48 minus 48 plus 9, which is 9 meters per second. So we know the velocity after 2 seconds and the velocity after 4 seconds. Part B, when is the particle at rest? So we have to think about what that means. When is the particle at rest? When it's not moving anywhere. That means its velocity has to be 0. So I need to solve my velocity is equal to 0. Let me write down my velocity. And we need to solve that equation to figure out when the particle is at rest. I would solve this by factoring. First thing I would do is factor out a 3. So I'm going to pull out a 3, which leaves a t squared minus 4t plus 3. This still equals 0. And now I would keep factoring. And I'm going to get a t minus 1 and a t minus 3. So I would set each piece equal to 0. We know this 3 is never going to be equal to 0. So we get t minus 1 is 0, or t minus 3 is 0. So the particle is rest at t equals 1 second, and again at t equals 3 seconds. So there were 2 moments where our particle stopped moving, just briefly. Now for part C, we want to know when the particle is moving forward. Well, the particle is going to be moving forward when the velocity is positive. That moves the particle in the positive direction. So I need to solve velocity is bigger than 0. The easiest way to solve that is to use the already fully factored velocity equation to solve where it's greater than 0. So my fully factored velocity was 3 times t minus 1 times t minus 3. And I want this to be greater than 0. The way I like to solve these is I put the two places where it's equal to 0 on a number line. And I just check in each of these 3 sections, I check some value in my velocity function to see if it's going to be positive or negative. So for example, over on this right side, I would think about seeing what happens when I plug in t equals 4. Well, if I plug 4 into this, my 3 is positive, 4 minus 1 is positive, and 4 minus 3 is positive. So all of that multiplied together is positive. If I plug in something between 1 and 3, let's just use 2. 3 is positive, 2 minus 1 is positive, 2 minus 3 is negative. Positive times negative is negative. And over here, well, I'm going to choose t equals 1/2 because I don't really want to plug in 0 where time hasn't even started yet, or a negative time, which doesn't make sense. So I'm going to choose 1/2 just to be safe. 3 is positive, 1/2 minus 1 is negative, 1/2 minus 3 is negative. Positive times negative is back to positive. So I know that my velocity is positive and therefore my particle is moving forward as long as my time is less than 1 or greater than 3 seconds. So we'll say it's moving forward when t is less than 1 or t is greater than 3. Now part D is going to get a little complicated. We want to find the total distance traveled in the first 5 seconds. So find the total distance traveled in the first 5 seconds. Now, the only reason this is a little complicated is because your first instinct might be, well, let's just plug in t equals 5 into my position function and t equals 0 into the position function and subtract the 2, and that will tell me how far it's moved. And that's kind of the right instinct. The only problem is our particle is moving forward sometimes and backwards sometimes, and just using the endpoints does not get us all of that information. So what we have to do to find the distance traveled is to first check how far it traveled going forward first, and then backward, and then forward again. So I know from time t equals 0 to t equals 1, my particle is going forward. And it moves forward f of 1 minus f of 0 in absolute values, meters. So we would plug this into our original function. The original function, remember, was t to the third minus 6t squared plus 9t. So this is equal to 1 to the third minus 6 times 1 squared plus 9 times 1 minus 0 to the third minus 6 times 0 squared plus 9 times 0. And all of that, when you simplify, gets you 4 meters. So in the first second, the particle moved 4 meters. I'm going to do the same thing for the next time interval. In between time 1 and time 3, So t equals 1 to t equals 3, we're moving backwards. And we're moving a total distance of absolute value, f of 3 minus f of 1. And again, you would get those values by plugging 3 into the original function and 1 into the original function and subtracting the 2. When you do that, you will also get 4 meters. And then all I have to do to finish this up is I know after time 3, we're moving forward again, but we only want the first 5 seconds. So I'm going to stop at t equals 5. We're moving forward. And we move forward a total distance of absolute value of f of 5 minus f of 3. And again, you get those by plugging 5 into the original function and 3 into the original function, subtracting the results, and take the absolute value. And you will get 20 meters. So this means that the total is the 4 meters that we got from time 0 to time 1, the 4 meters from time 1 to time 3, and the 20 meters from time 3 to time 5, for a total of 28 meters traveled. All right, and then the last part to this problem, find the acceleration of the particle after 4 seconds. So now we have to remember how to find acceleration. Our velocity was the first derivative of our position. Acceleration is the second derivative of position. So I need to take the derivative of my velocity to find my acceleration. A of t equals v prime of t. So let me quickly remind us what the velocity was, and then we can take the derivative to find our acceleration. Our velocity was equal to 3t squared minus 12t plus 9. And so my acceleration is the derivative of this. Using my constant multiple rule, my 3 gets to stay. The derivative of t squared is 2t to the first, using my power rule. Then using my constant multiple rule, I have my minus 12 staying. The derivative of t is 1. And then the derivative of 9 is 0. Simplifying this, my acceleration is equal to 6t minus 12. And so my acceleration after 4 seconds is 6 times 4 minus 12. That's 24 minus 12, which is 12 meters per second squared. All right, so that's all for this video. We learned a little bit of how to make our derivatives a little easier. We've learned our power rule. We've learned how to add and subtract different terms while doing the derivatives. We learned our constant multiple rule. All of these make our derivatives much, much easier compared to the definition of the derivative. In the next video, we're going to learn more rules of differentiation. We're going to learn the product rule and the quotient rule, which are a little more complicated, but it's still way easier than using the definition. So stay tuned for that video. If you have any questions, feel free to drop them below. Or if you are a current student of mine, you may email me your questions or come to office hours, and I'd be happy to help. I'll see you next time.